Hello, everyone. Thanks for attending this session. I'm going to talk about how we accelerate the data analysis of our output simulations of the brain. This is the outline of the presentation. I'm going to first start with a little introduction. I work at the Blue Brain project. It is a Swiss initiative that targets the digital reconstruction and simulation of the brain. It's hosted, or it's based in Geneva, in Switzerland. We are a group of a bit more than 100 people. And one of the cool things for me of the project is that it groups a lot of people from different backgrounds. For example, of course, we have biologists, because this is the basis. But also we have computer scientists like me, or we have physicists, mathematicians, or even graphical designers. So to put you a little bit into context, neuroscience has many study areas like neurophilosophy, neurology, neuropsychology. Probably you just use the neuro prefix and you find a word and you'll find a neuroscience study area. In the context of Blue Brain, we are at the top corner, which is the Computational Neuroscience branch. In this branch, we use mathematical models and also theoretical analysis and abstractions to understand how the brain works. Then these models are, with the use of computers, are simulated and are validated. One of the key target contributions of the project is to help scientists understand how the brain works. For example, not that long ago, we were able to digitally reconstruct a small region of the brain, and then simulate the behavior. And once we have the results, we can go to the laboratory and compare this with in vitro or in vivo experiments, and we could verify that the results match. So this is a very important step because through the use of supercomputers and the simulation of the brain, we can provide new tools to the scientists to understand how the brain works, and it opens the possibility to do some experiments that are just impossible in the laboratory, but with the use of supercomputers, we can do that. Also, we believe that the advances that this can bring can help, of course, understanding better brain diseases, but also it can contribute to other fields like the neurorobotics, for example, or even AI in the future. Oops, sorry. Now, brain simulations can happen at different detail levels. So, for example, we can go to the highest level, which would be using point neuron models. In these models, we have each neuron is represented by a single entity, which is like a point, and then these points are connected between them to build the neural network, and then the simulation happens at this level. But also we have more detailed models, like morphologically detailed neurons, where each neuron has its own morphology, so you can specify the shape with all the branches. Then these branches are divided into different sections, and these sections is like the minimal unit that's going to be simulated. Or we can go to like the most detailed level, which is the subcellular level, where we simulate how the molecules move from one side to the other and all these kind of things. Three common simulators are nest, neuron, and steps, respectively, for these three levels. If we pick different experiments that scientists have done with these models, we can, well, I'm not going to go through all the details of the lower rows of the table, but my main point is that depending on the level of detail, you can have a more complex simulation or less complex. So in the end, like for example, if you look at the last row of the table where I tried to normalize the different data from the different experiments, you can see that if you go from the less detailed model to the middle model, it's like you need like a factor of 100, so it's more complex, but then if you go to the molecular level, this is like hundreds of millions. So the level of detail really makes a difference in the complexity of the models we are simulating. At BlueBrain, we have collaborations with the developers of the different simulators, but mostly all the scientists in BlueBrain use the neuron simulator, which is the one in the middle. So I'm going to focus my presentation mainly on this simulator from now on. So let me talk a little bit about our motivation. This is the general workflow that we have when we want to simulate a part of the brain. The first thing that the scientists have to do is to configure what they want to simulate, like the number of neurons, the type of neurons they want to use. They have to set the amount of biological time they want to simulate, and so on. Then they can run the simulation. The simulation usually takes some time, sometimes more than what the scientists would like to, and it periodically records the data and the state of the neurons into one or different files. So once the simulation is finished, we have different tools that are able to read these files, and then we can visualize what happened, or we also have like scripting, some scripts that can analyze the data, can produce plots or histograms, or the different things that the scientists need to see what happened during the simulation. So our challenge is that the brain simulation can produce gigabytes or terabytes of data very quickly. For example, if we take a plastic neocortex simulation, and we say we want to record one variable, which is like one parameter of the simulation, and we want to simulate the behavior of the brain for 30 seconds, and we are using 31,000 neurons, which is a very small subset, as the human brain has billions of neurons. This would generate like 50 gigabytes of data. But the thing is that this is not enough. The scientists don't want to record one variable. They want to record many variables. And 30 seconds of biological time is too short. They want to record for minutes or ideally hours. And then 31,000 neurons, yeah, as a starting point, it's good, but they want more than that. So if you multiply these times 50 gigabytes, you can quickly reach terabytes of data. The current status is that the scientists write Python scripts. They like Python, and they usually don't want to know about anything else. So we are restricted to this. Well, Python is easy, right? So that's fine. The thing is that these Python scripts are usually written serially. They don't know or they don't want to spend time in parallelizing their scripts or making them more efficient. For this, we have different tools based on Python as well that can exploit the parallelism on the node. So we can make them things a bit faster and a bit better and more optimal. But the existing tools don't scale across a cluster. They just exploit the node level parallelism. So this model or this situation, like it works fine for now, but it's not sustainable in the future. So we want to find a solution to improve this situation. So in short, our requirements is that whatever solution we came up with, it must be Python friendly. That's, I would say, our top one requirement. It must be scalable because we need to analyze gigabytes or terabytes of data. So we need to scale up through like several nodes, a supercomputer, or big machines. And also, we have to remember that this is the simulation workflow. And we are at one of the very last steps in the analysis and filtering part. So whatever we do, we cannot change this workflow because all the chain will be impacted. Like all the tools that we use are going to be impacted. And we cannot afford changing all the tools because like at the very last step, we need some, I don't know, some detail. And also, we have to be compatible with the existing tools, and we cannot change the scientist's workflow that much because they are used to something, and if we ask them to change a lot, they're not gonna use it. They're gonna stick to what they know. So let's see how we can do that. This is the current status where we have a GPFS file system. The simulator writes the output data in a binary format. It uses a custom layout. So the data is stored there. And then we have the scientists, scripts, and Python tools that access this data. They read it, and then they do some kind of analysis or visualization. So our proposal is to put the Spark cluster in the middle in a way that the scientists, scripts, and the Python tools can query the data directly to the Spark cluster where the data is going to be loaded. And also, if there is some type of analysis or computation that has to be done, we can do it in the Spark cluster, which is going to be more scalable and more efficient. One of the things that we are missing here is that we need a binary file reader because we are using a custom format, so there is no native Spark reader, and we have to provide it. So Spark seems a good option for us because it has Python support. Also, it is scalable across large clusters. We could do something to hide it from the final user, so this is a very good thing. It fits our type of analysis. It also has SQL support, which may be helpful for some type of analysis that we may do in the future. And also, last but not least, it is compatible with the systems and the machines that we have on site. So this is also very important. On the other side, there are not so very good things about Spark that we have to be aware of. The first one is that because we are using Python, the scientists are used to NumPy arrays, and most of the data structures they use are NumPy arrays. So if we are using RDDs, this is fine because they are supported, but if we are using data frames, there is no support. So we would have to convert the arrays into some other structure. There are also some performance penalties that we have to be aware of, which is that we don't have a native reader, so we will have to implement one, and this for sure is going to introduce some kind of overhead. Also, the fact that the Python layer of Spark is implemented on top of the Java layer, this creates some inefficiencies, especially when we define user-defined functions, because the data must be copied back and forth. And we're gonna need that for sure. And also, the last thing is that we have a GPFS file system, which is not the optimal type of file system for Spark, where I think HDFS would be much better, but our file system is GPFS, and we cannot change that. So we have to be aware of these limitations. But still, we think it's worth to investigate how Spark can behave with our use case and how we can make the most of it. So because Spark offers a lot of design options, what we did first is we made a list, and we wanted to evaluate which are the options that fit better our use case. So we started the evaluation. First of all, we wanted to see if we should use RDDs or data frames. If you read the usual websites, they tell you to use data frames because this is the future. But of course, our default data layout are NumPy arrays. And since they are not supported, we still wanted to try how RDDs behave in our use case. Also, we wanted to see how data partitioning works. Is it better to let Spark partition the data, or should we use our own partitioner? Also, which data containers should we use? As I said, we are used to NumPy arrays a lot, but also we have to consider other containers that are supported in data frames, like byte arrays and Python lists, for example. And lastly, we wanted to see if, like, our default format is what we call the BBP binary format, which is the format that the simulation outputs and writes the data. But also we wanted to see if there is another format which is more like in the Spark ecosystem that can fit our use case and can give some benefit. If you do the math, this is like more than 20 combinations. I think it is not feasible to evaluate all of these in a reasonable amount of time. So what we did is we picked several combinations, which are the color code on your right. And then we evaluated these combinations. So in terms of implementations, we have 4 different implementations. The blue one is the one using RDDs with automatic partitioning, and it's holding NumPy arrays. I think this is like the most basic one and simple one to implement. The second one is the green one. It's similar to the RDD implementation, but this time, instead of using the automatic partitioning, we use a manual partitioning based on what we call the GID. The GID is the neuron ID, or like the neuron number. So the information of each neuron will be separated. And we have 2 another implementations for the data frames. The first one uses also automatic partitioning, and the NumPy arrays that we get originally from the binary file are converted into byte arrays in binary. And then the last one is also using data frames with automatic partitioning, but the NumPy arrays are translated or are converted into Python lists. Also, we distinguish if the data source comes from our BBP binary format or the Parquet. So in total, we have 8 combinations. If you see, these colors are going to be used throughout all the slides. They are consistent. And also, the dark colors are associated to the BBP binary format, and the light colors will be associated to the Parquet format. So how do we evaluate if Spark is a good solution for us? Well, first, I'm going to explain how the data format looks like, more or less. This is the structure that the simulator outputs. It can be seen as a matrix where we have rows, and each row represents the state of all the neurons in one time step. And then within each row, it has the information of each neuron. Well, if I say GID, it's also neuron. We say them distinctively. So we talked to several scientists in our group, and we identified different queries or different analyses that they do usually. The first 2 well, they are like reductions. So they take the data, they group it into, like according to several criteria, and then they reduce the results. This is like one operation. The other operation is like they take the data, they do some computation on it, and after that they also group the data according to some criteria, and then they reduce the results. The grouping criteria is always either by time step or by neuron. So it either groups the data by rows, if it's by time step, or by columns, if it's by neuron. So in the end, we defined 4 different types of analysis, which we list here, which is reduce by GID or by time step, and then compute by GID or by time step. This is the platform where we evaluated our implementations. It's 40+ node cluster, It has InfiniBand network. It's connected to the GPFS file system. Each node is based on Skylake, and it has, the nodes are quite powerful. They have almost 400 gigabytes of DRAM, and also each node has 2 terabytes of SSD local storage. These are the software versions that we used, and regarding the runtime configuration, we would like to highlight that we had exclusive access to the nodes that we were using, but we didn't have exclusive access to the machine. So mainly the network and the GPFS access were shared with other users at the same time. And also we launched the Spark cluster there in cluster mode, but we always use a separate node to run the Spark master, so that we give to each Spark worker the resources of one node. By default, unless stated otherwise, we use a dataset size of 2 terabytes. So the first test we did was to find out what's the memory footprint when we run Spark on one node. So we took 2 nodes, and one was running the Spark master, the other one was running the Spark worker. And we were checking when we were executing our application, and then we were checking what's the memory usage on the worker node. So the different steps that we have in our application are the ones listed on the horizontal axis, which is first we log into the node, then we call the start slave script, then we open the PySpark shell, then we load the data, the simulation data. In this case, we used reduced file size of 47 gigabytes. And in this step, we ask Spark to cache the data so that it resides in memory. After that, we run the 4 data analyses, one after the other. Once we finish, we ask Spark to unprocess data, and finally, we quit the PySpark shell, and we stop the slave. What we can see here, if we look at the blue area, is that this is the one that stays closer to the real dataset size, which is 47 gigabytes. This is around between 50 and 70 gigabytes. But the other implementations, like any other, need at least from 3 to 6 times more memory. So one of the problems that we had here is for the implementations using data frames with Python lists, we could not finish the experiments because they crashed due to lack of memory. So we discarded this implementation for the next tests. The next test we wanted to run is we wanted to see what's the execution time of loading, or what's the cost of loading all our simulation data into a Spark cluster. Here, what we can see is that the dark lines, which are the ones that correspond to the BBP file format, they take more time, and actually they don't scale. It's the opposite. This is because we have, GPFS is too overloaded. We have too many processes accessing the same file at the same time, and it doesn't scale. In the case of Parquet files, because when we created the Parquet files, we divided the data into smaller chunks, so we end up having thousands of files. Here we can see that the performance is better because the different processes are going to read different files, so GPFS can handle this better. Probably, I don't know if we were using HDFS, this would change, but in the end, GPFS is what we have. And if we compare this to the existing tools, for example, if we take the best case, we get like 100x speed up. So in the end, it's not that bad. The next thing we wanted to evaluate is the performance of the reduction operations by neuron or by time step. Here, what we can see is that if we look at the left-hand side, the performance of the green lines, which correspond to the data that's manually partitioned, they take less time because we believe that here the manual partitioning does a better job and needs like less communication between nodes when we do this type of analysis. And the pink lines take much more time than the others because there are some data conversions involved. So this gives some performance penalties, which are the pink lines are the data frames using binary byte arrays. In the case of reducing data by time step, because we run one experiment after the other, we believe that some of the partial results were cached. So here we cannot see like any real difference between the different implementations, but also this gives us an idea that if we are able to run different analyses that have some parts in common, we can also accelerate and get advantage of running one after the other. Finally, we have the results of computing, doing some computation on the data and then grouping by GID or by time step. The results here are similar, and I think I'm running a bit out of time, so I'm not gonna comment a lot on them, but we can discuss it then after offline if you want. So finally, the conclusions are that Spark improves our data analysis. In the best case, we can get up to 130x speed up, so that is good. And also, we believe we can improve these numbers if we do a bit more work on this. There are a few corner cases that we need to investigate on our side because we cannot really explain why the performance is what we get. And also, like, one of the main conclusions is that the design decisions can impact a lot the final performance. So this is really one thing that we have to evaluate before we really implement one solution. And finally, well, Spark, I think it does a good data partitioning, but if you have more knowledge on the data you're storing, I think if you use a manual partitioning, you can do a better job. And apart from that, so we would like to open like some discussion points. The first one is that we really lack the support of NumPy in data frames. Well, this may change in the future because this morning I was talking to Lee after his presentation, and he told me that in Spark 2.3 it is possible to use NumPy arrays into data frames and defining them as arrays. Yeah. So I have to try that. In the future, I may remove this point from this slide. And also, I believe that one thing that would be useful for us is the ability to control the number of executors that we have on the node. Because, for example, as you saw before, when we are loading the data from GPFS, we have a huge impact performance. If we could tune the number of executors that we have per node and set it to like 1 or 2 or a few per node, we believe that the performance of loading the data would be much higher. But then at some point, we want to use the full node with all the resources and increase the number of executors that we have on each node to do the computations. So if we could do this at runtime, because now you can set it when you launch your Spark cluster, but once you've launched the cluster, you cannot change that. So we think that that this could be also a very good point for us. And well, we are open to talk to other people that have found like the same issues or similar issues, and we are interested and happy to listen to how they have worked around them. Finally, like some acknowledgments and references from the data that I provided in the presentation. And thanks for your attention.